Okay, students, now that we've covered how to calculate this new concentration called molality, we're going to end up using this molality in determining some colligative properties and changes in colligative properties of solutions. And just as a reminder, colligative properties are those properties of solution that depend upon the number of solute particles that are dissolved in the solution. And they are independent or do not depend upon the identity of the solute itself. So let's fill in this gap. Colligative properties, one of the principles here is the number of particles dissolved in a solution can change the solvent's freezing point and boiling point. So I'm going to be written here a little bit, so I'll say the number of dissolved solute particles. So the number of dissolved solute particles in a solution is going to have an effect on the freezing point or boiling point of a solution. So let's think about what that means. You've got a glass of water and you put it in the freezer. And it's going to take a certain amount of heat loss before that glass of water freezes. Well, if you dissolve some salt in that glass of water, then those dissolved solute particles will change the solvent's freezing point. So, something to think about when we're thinking about how dissolved solute particles affect freezing points and boiling points of solvents. Every solvent has its own unique proportionality constant. We're going to talk about proportionality constant here in just a moment. That relates the effect of these dissolved particles on the boiling point or freezing point. For this chapter, we're not going to be dealing with other solvents other than water. So we're just going to be talking about changing the freezing points and boiling points of water, although you could do it for other solvents as well. And for water, the boiling point elevation constant, K sub B, is this number right here, 0.52 degrees Celsius per molal unit. And the freezing point depression constant, K sub F, for water only, is 1.8 degrees Celsius per molal unit, okay? So with those two numbers in mind, let's move on and actually deal with some problems when we are changing boiling points and freezing points. So a couple of trends that you need to be aware of. The more solute particles that you dissolve in a solvent means that the solvent's boiling point increases. So the boiling point goes up, right? Boiling point increases when you dissolve more solute particles in it. And down here, the more solute particles dissolved in solvent means that the solvent's freezing point decreases. So the freezing point drops, it decreases. And I want you to notice that they are not heading in the same direction. If I take pure water, I know that its boiling point at 1 atmosphere of pressure is going to be 100 degrees Celsius. But if I start to dissolve solute in it, like salt, then its boiling point is going to end up increasing. It's going to be higher than 100 degrees Celsius. I know for pure water at 1 atmosphere of pressure, its freezing point is at 0 degrees Celsius. But if I dissolve solute particles, like sodium chloride, in the water, then it will decrease the freezing point, and its freezing point will drop. It will be lower than 0 degrees Celsius. So there is an equation. There are equations that help us determine these changes in our colligative properties of these solutions. And the equation that you need to know for the boiling point is that the change in temperature, the delta T, for the boiling point, sub B, so the change in the boiling point temperature can be calculated like this. And I'm going to include the version of this equation that includes this little letter right here. It's an I. Okay, and I'll explain what that is in just a moment. Is I, lowercase I, capital K sub B, and then the molality. Okay? So I have three terms here. Lowercase I, capital K sub B, and then molality. So what are these? Well, we know molality because we've just covered it. That's the number of moles of solute divided by the kilograms of solvent. Capital K sub B is this boiling point elevation constant. It's this number right here. This is a constant right there. So what is I? I is called the Vant Hoff factor. The Vant Hoff factor. And what is the Vant Hoff factor? All the Vant Hoff factor is the number of particles in solution per formula unit. Okay? So what in the world does that mean? Well, let's think about sodium chloride. We know that sodium chloride is an ionic salt. It dissociates into its ions, so for NaCl, it breaks up into Na plus and Cl minus, right, in solution. So there's one particle in solution and there's two particles in solution. So the Van Hoff factor for NaCl, the I equals 2 because sodium chloride dissociates into two particles for every formula unit. Okay? Another way of writing this equation is omitting the I, leaving the Van Hoff factor out. So let me explain how you can write this equation, and it can be a different equation, leaving the Van Hoff factor out. If you leave the Van Hoff factor out, then the delta T sub B equals KB M, and in this case, the molality doesn't just mean the moles of solute, it means the moles of solute particles. So for every 1 mole of NaCl you had dissolved, you would have 2 times that number of particles, right? So both of these equations work. Whether you include the I in there, the Van Hoff factor in the equation, or whether you don't, you always have to make sure that you are considering the number of particles that are in solution. So in this case, I'm making explicit the fact that we need to multiply the molality of the solution times the number of particles per formula unit once it dissociates in the solvent. Okay? So with that in mind, notice also that this is going to be a positive result. The Van Hoff factor is either going to be 1 or some other positive number. Molality is going to be a positive molality. K sub B is a positive 0.52 for water. So I get a positive delta T. What does that mean? Notice that this is the delta. If a delta is positive, it means that you are increasing your temperature. So once we calculate delta T, then we have to add it to the original boiling point, right? So this delta T is not going to give us our new boiling point directly. It's going to give us the change in temperature from the original boiling point. So with that in mind, I've given you a sample problem here. What is the boiling point of a 0.24 molal solution of aqueous calcium chloride? So pay attention to a few things here when you do this problem. You're asked for the new boiling point, not just to calculate the change. So you're going to have to calculate the change and then add it to 100 degrees Celsius. There's your molality. There's your lowercase m. We're going to get K sub B from this value right here, the boiling point elevation constant for water. So where do we get the Vant Hoff factor? Well, it's going to be the number of particles in solution per formulate unit. Calcium chloride, when it dissolves, it's going to dissolve into calcium ion. And notice it's going to dissolve into 2 chloride ions. Right? So what is the Vant Hoff factor for calcium chloride? 1, 2, 3. So the Vant Hoff factor for calcium chloride, 3, because there are going to be 3 particles that are dissolved in solution for every one of these formula units. Okay? So with that in mind, go ahead and solve this problem. Pause the video, complete the problem, and when you're done, I will work through it. Okay, coming back to this problem, what is the boiling point? Well, our boiling point is going to be whatever the original boiling point was plus the change in temperature, right? So the new boiling point equals the boiling point of the pure solvent plus the change in temperature of the boiling point that happens here, right? So what is the change in boiling point? Delta T sub B. So let me just make a new calculation here. Delta T sub B equals the Vant Hoff factor, which for calcium chloride is going to be 3 because it dissociates into 3 particles. Kb, the boiling point elevation constant for water, is 0.52 degrees Celsius per molal unit. And then I'm going to, let me use parentheses here rather than those dots to signify multiplication. Okay, 3 times 0.52 degrees Celsius per molal unit. And then mercifully, they've already given us the molality, so I don't have to calculate what the molality is. Okay. And when I do that math, 3 is an exact number because it's the Vant Hoff factor, exactly 3 particles. So 2 sig figs, 2 sig figs, my answer is going to be in 2 sig figs. The delta T is 0.37 degrees Celsius. Now, one of the challenges is that many students will get to this answer right here, and they will stop. They will circle that and say, there's my answer. But that's not the answer. That is the change in boiling point. So the new boiling point is the original boiling point when it was pure solvent plus the change, right? So we know that the original boiling point is 100.000 and so forth and so on out, as precise as we need to make that. The delta T is 0.37. So the new boiling point is 100.37 degrees Celsius. And there is our answer. The new boiling point of this aqueous solution if we have a 0.24 molal concentration of calcium chloride, that is its new boiling point, 100.37 degrees Celsius. So notice again that the boiling point was elevated, was raised, was increased. All right, Moving on, we're going to do another similar problem. And in this problem, we're going to calculate the new freezing point. So when you add solute particles, it depresses or decreases the freezing point. So one of the things to think about here is, why in the world is this happening? And one of the ways that it may be helpful to think about this is to think about solvent molecules being sort of like puzzle pieces. So for example, if you have water as a solvent, then each water molecule is sort of like a puzzle piece. And to freeze, all of those puzzle pieces have to arrange themselves in perfect arrangement to form an ice crystal. But when you dissolve solute particles, think about what would happen if you're trying to put together a puzzle and you have a bunch of sand grit on the table. Here you are trying to put puzzle pieces together, and the sand grit is all in between them, right? So the sand grit would prevent or make it more difficult for your puzzle pieces to come together and interlock. And that's kind of what is happening when you have solute particles dissolved in a solvent. The solvent molecules are trying to come together and lock into a crystalline structure, but the solute particles are getting in the way. And so rather than being able to lock into a crystal structure at, for example, 0 degrees Celsius, you have to push much lower than that, or significantly lower than that in temperature, to finally be able to get them to lock together, because the solute particles are getting in their way. So the freezing point will decrease the more particles you have dissolved in solution. So the equation for calculating the new freezing point is very similar to calculating the new boiling point, with two notable exceptions. The first is that we're not going to be using the boiling point elevation constant, but we're going to be using the freezing point depression constant. And the delta is going to end up giving us a negative number, because we're going to be dropping the temperature. So the change, the delta T for the freezing, the change in the freezing point, equals, so we put a negative sign there to make this a negative value so that we are depressing the freezing point. Negative Vant Hoff factor times freezing point depression constant times the molality, okay? So we'll end up getting a negative delta. That means that we are changing it by lowering it. Negative I K sub F M, okay? So with that in mind, and without any more coaching at this point, I'll ask you to solve this freezing point depression problem. What is the new freezing point of a solution of sodium chloride in water that has that concentration, 0.15 molal? So give it a shot. You've got the equation here. You know how to plug those values in. Pause the video now, see if you can finish that, and when you're done, resume the video and I'll work through it. All right, coming back to this problem. And fortunately, we got a little bit more space here on the page to work with this, so we're not going to be quite so jammed up as we were up here. In my next version of this, of drafting this workbook, I'm going to have to leave a little bit more space up here for this problem. But for this problem, we've got a little bit more space. So what is the freezing point? So the freezing point, the new freezing point, is the freezing point of the pure solvent, of pure water, plus the change in the freezing point. We know that that is going to be a negative value, right? So this is going to end up being, the new freezing point is going to be lower than the original. So we know that the pure freezing point of water is 0.00 degrees Celsius plus our delta T. And our delta T, I can just plug in these values. So it's a negative Vant Hoff factor for this sodium chloride. What is the Vant Hoff factor for sodium chloride? It's 2, right? Because it separates into 2 ions in solution. So it's a -2 times freezing point depression constant, 1.86 degrees Celsius per molal unit. Times the molality, which fortunately they've just given me outright and I've not had to calculate that separately, 0.15 molal. Okay, so 0.00 degrees Celsius originally, plus this new delta T, right? And if I do this math, -2 times 1.86 times 0.15 equals. So plus a negative 0.558, and I need that rounded to 2 sig figs, 0.56 degrees Celsius, right? So what is my new freezing point of this solution? It's my original freezing point plus the change. The change is a negative value, so I will subtract this, and I will get negative 0.56 degrees Celsius. And that is my new freezing point. Notice that my new freezing point is lower than the original freezing point for the solvent, because by adding dissolved particles, I have depressed or lowered the freezing point of this solvent. So let's take a moment and reflect about how we can see this happen in our everyday lives. You may have heard or you may have experienced when municipalities like cities put salt on roads in the winter to keep the roads from icing over. So let's think about how that takes advantage of the freezing point depression as a colligative property of water. Normally, water would freeze on the roads at 0.00 degrees Celsius. But if they can add a little salt to the roads, then they lower the freezing point of that water a little bit, which means if it's a little bit colder than 0.00 degrees Celsius outside, then the water on the road might still be in liquid form. It might not have frozen yet. Obviously, when you dump a lot of salt on a road, the molality concentration is going to be much, much, much higher than 0.15 molal. So you would have a much larger change in the freezing point depression. And having a few degrees lower freezing point for water may make the difference between having ice on the road versus having liquid water on the road. So that's how we calculate boiling point elevation and freezing point depression. I just want to remind you that these equations can be reported in slightly different forms. You may see the equation that does not have the I, the Vant Hoff factor, explicitly written. But it's still the same math, even if the I is invisible. When the I is there, it represents the number of particles per mole of solute formula in solution. When the I is not there, the Vant Hoff factor still has to be considered because it's now considered part of the molality, because the molality is then written in terms of the molality of particles in solution, rather than just the molality of formula units in solution. So whether the I is there or whether it's not, you still have to use that factor in your calculations to factor in the number of particles per mole of solute that is being dissolved. Secondly, always remember that boiling point increases when you add solute particles, and freezing point depresses or lowers as you add solute particles. So they do not head in the same direction. They head in opposite directions when you add solute particles. And be especially careful to make sure that you're using the correct constant. You'll be given a boiling point elevation constant and a freezing point depression constant. Make sure you use the correct one. And finally, make sure that your delta T is actually heading in the correct direction, so that if you do this math, you end up with a new freezing point that is lower than your original freezing point. Okay.